Let us derive the relation between the eigenvalues lambda and m. Lambda being the eigenvalue of j square, m being the eigenvalue of jz. Now I have already derived this product j plus j minus and j minus j plus. So using these two products I have found equation 20, and now I am going to find out the this thing in the state lambda m. Lambda m being the common eigenstate of j square and jz. Now using equation 20 here, I have obtained this relation. This 2 is a scalar, so I can take it outside. These are the eigenvalue equations for j square and jz. I am going to use these two eigenvalue equations here in the right hand side of this equation. J square lambda m will give me lambda m. Lambda is the eigenvalue, this is the eigenstate. And jz square operating on lambda m will give me m square, and this is the eigenvalue m square, and lambda m will be the eigenstate. As this is eigenvalue equation for jz, so jz square will give me m square. So I have arrived at this equation. These are the eigenvalues, which means these are just values, some numbers, some scalar quantities. So this has nothing to do here. So they can be taken outside. And using the orthonormality property of lambda m eigenstates, I am free to write lambda m, that is the inner product of lambda m with itself, as equal to 1. So my equation 21 is now this, which is this equation. So right hand side of this equation is 2 into lambda minus m whole square. Now I need to find out the value of the left hand side and equate it to 2 into lambda minus m whole square. First I will find out the value of j plus j minus in the lambda m state. So here is the calculation. This is j plus j minus sandwiched between lambda m states. Now I am defining this j minus lambda m, a new state which is phi. This is phi ket, so phi bra should be just like this. Operator algebra has taught me this. And as these phi are the eigenstates, so inner product of phi with itself, that is phi into phi, that is the scalar product of phi, that must be greater than equal to 0, because this defines the length of the state, which must be a positive quantity. So this thing must be greater than equal to 0. So basically what we have obtained is a value of this quantity in the lambda m state, which gives me that the value of this in lambda m state is equation 21, which is 2 into lambda minus m whole square. So as we have already found that this quantity is greater equal to 0, which gives me equation 22, which is the restriction of lambda and m square. This restriction is lambda should be greater equal to m square. Now this j plus minus, these operators are called ladder operators. This j plus minus, just for recall, this is a summation of jx and jy. Now we will prove why these are called ladder operators. We will be considering this eigenstate, which is j plus lambda m. For the time being, we consider this as just a state. So on this state, the j square operator is operating. As jx contains jx and jy, j plus equal to jx plus ijy, j square commutes with jx and jy both. So j square commutes with j plus also. So from the commutation relation of j square and j plus, I am obtaining this. J square operating on this state will give me lambda h cross square, and the eigenstate is lambda m, because this is the normal eigenvalue equation for j square. Now this tells me that this j square operating on this eigenstate, which is j plus lambda m, gives me the eigenvalue lambda m h square, lambda h cross square, I'm sorry, and the eigenstate is j plus lambda m. So this is the eigenstate and this is the eigenstate. Operating on this eigenstate, I am getting the usual eigenvalue of j square operator. So this is my equation 23, which tells that if j plus lambda m is not a null ket, is not a zero vector, we will get this equation number 23. Again, we are considering the operation of jz on this same eigenstate. The state is j plus lambda m. First, I have considered the operation of j square. Now, I am considering the operation of jz on this j plus lambda m. Now, as jz and j plus do not commute, and just for your convenience, I have written again the commutation relation. I have already proved these commutation relations. So, I am using these commutation relations here, and I have obtained equation 24. This step is I have used the commutation relation between jz and j plus. Now jz operating on lambda m gives me lambda m h cross. This h cross is just a number, so here it stays on the left hand side. So eigenstate is j plus lambda m. Here this mh cross is also a scalar, a value, so it can be taken here, and the eigenstate is j plus lambda m. So for the j plus lambda m eigenstate, I can write this equation 24, which tells me that operation of jz on this eigenstate j plus lambda m gives me the eigenvalue m plus 1, which is greater than the previous value of m by 1 unit. So we can say now that this j plus lambda m is having this eigenvalue equation, which is equation 28. Eigenvalue is c plus. As the eigenvalue m increases by 1 unit, so now this m becomes m plus 1. So operation of j plus on lambda m gives me a new eigenstate lambda m plus 1 with length of this eigenstate as c plus. Now we need to find out this c plus. This serves as an eigenvalue of this equation. Now it is quite evident that lambda m and lambda m plus 1, these are vectors along the same direction, because the length is only changed. As the length is changed only, the direction of the vector does not change. We are making dual conjugation of equation 28, which gives me this equation 29, because dual conjugation will make this bra vector lambda m as ket vector lambda m, and this j plus will become j plus dagger. We normally consider these eigenvalues as complex conjugate, so c plus star is the complex conjugation of this c plus, because these eigenvalues are generally they are complex numbers. That's why I have written this as c plus star, and this bra vector lambda m plus 1 becomes the ket vector lambda m plus 1. This is equation 28. Now I need to multiply equation 28 and equation 29, and let's see what happens. So I'm getting this. These are normalized vectors, so this thing gives me 1. So I'm getting only c plus mod square in the right hand side. Left hand side I have obtained this one. Now I have applied equation 15. You can check equation 15 from my previous videos. So in place of j minus j plus, I can write using equation 15 j square minus jz square minus h cross jz. So operation of j square or lambda m gives me lambda h cross square, that is the common eigenvalue equation for j square. Jz operating on this state will gives me m h cross. So operation of jz square will give me m square h cross square, and then again operation of jz will give me m h cross. H cross is already there. All these are scalar quantity, so we can write this out of the from the middle of the states. So I can write it here, and left is lambda m, that is the scalar product, inner product of lambda m with itself, and as these are normalized, so this thing will give me 1 using the orthonormality condition. So here is the thing, and c plus is nothing but root over of lambda minus m square minus m h cross. So the eigenvalue of these equations becomes equation 30, which is c plus equal to root over lambda minus m square minus m h cross. So using this equation 28 and 30, we will be able to evaluate the new eigenstate, which is denoted by lambda m plus 1. Lambda is the value of the angular momentum, m plus 1 is the projection of this angular momentum, and the eigenvalue is this one. So we are getting a new eigenstate from this lambda m by the help of operation of j plus, and the new eigenstate has a new m value increased by 1 unit, and the eigenvalue for this particular state is this one.